All right, we have talked about velocity and acceleration in quite a few different orientations. Now I want to talk about the forces that cause those accelerations. So if you visualize then the force that is applied to a rigid body, if the force goes through the center of gravity of that rigid body, it's going to have a mass times acceleration that is in the same line as the force. In other words, these accelerations and the forces are vectors. The acceleration has to be lined up with in the same direction of the force that is causing that acceleration. However, if the forces are in the same line, however, but they're offset by a slight distance, a distance d, we can still look at the line and we can say that, well, we have a force in that direction, therefore we must have an acceleration in that direction. However, that distance d here is going to cause a little moment about the center of gravity, such that that moment is not going to cause an angular acceleration. So we get a general set of equations and general understanding is that the forces in the direction of a particular direction cause an acceleration in that direction, and that it is dependent on the mass. In other words, the greater the mass, the less acceleration. So the mass resists acceleration, if you will. The moment about that center of gravity then causes an angular acceleration, which is dependent upon the mass moment of inertia. That is the letter I, and I also resists angular acceleration. And we're going to talk more about angular acceleration as we go forward and mass moments of inertia. All right, so in the beginning then, if we sum the moments about the center of gravity, and if we have all our forces applied through the center of gravity, it faces pretty easy. However, there are many times when we don't want to sum the moments about the center of gravity. In other words, we may want to consider rotation about a different point, or at least use a different point for using for our moment summary. So consider this. If you have a different point that we want to consider, what we'll have is a mass times acceleration vector that we had on our first picture, but the mass times acceleration vectors always act through the center of gravity. In other words, if it's moving in this direction, it's the center of gravity that's moving in that direction, and there will be a mass times acceleration of the center of gravity in that direction. We may have some forces that cause mass times acceleration of gravity in this direction. Again, the MA is a vector, and it always acts through the center of gravity. So we will draw these vectors, the MAG and the MAGY, MAGX and MAGY, as emerging from the center of gravity in the direction of their acceleration. However, they may be separated by a distance from the actual point of rotation or the actual point that we want to consider. And we're going to call that distance the x bar, and in the x direction, and the distance in the y direction, y bar. So that our moment equation about p then becomes sum of the moments about p is equal to the mass times acceleration vector, which is going to be this, separated by the distance in the y direction. So if I'm having mass times acceleration in the x direction, it would be separated from distance p by that distance y. So that's that term right there. We'll also have a mass times acceleration in the y direction separated by a distance x, which is that term. And we'll also still have a rotational element. Again, these are just the results of the forces moving in those two directions. We'll have accelerations in that direction, and acceleration in the x direction, and acceleration in the y direction. However, we still have a rotational element, which is the alpha times the mass moment of inertia. This is now called the generic kinetic equation. In our book, there's a script M that is used to describe this kinetic moment equation. I would generally not use that because I'll just use the terms. But anyway, these are terms that are used to describe the motion and the mass times acceleration and the rotation about some point other than the center of gravity. And as we walk through this, it'll be easy to see how we use those things. Okay, so that equation looks a little cumbersome, but these three equations and then this equation will be our four basic equations for studying rigid body motion, rigid body acceleration, and rigid body rotation. Now again, this equation will be used quite a bit, and it looks a little cumbersome, and there are some special conditions that we'll consider that will make that equation a little bit easier to use. The first special condition is called translation. We're just going to be moving in a straight line, and in that case, we will not be rotating. Quite a few different examples where we'll be using translation without rotation. So it'll be rectilinear translation, meaning in one direction. If it's not rotating, that means the CG is not rotating, and this term IG alpha becomes 0. We'll still need to find the forces in the x and y. We'll still need to use those first two equations. However, if we look at the moment equation, some of the moments about g, if IG alpha is equal to 0, the right side of the equation is equal to 0. And if we want to solve moments about p, again, we still have to have those two vectors and multiplied by their distances. However, the IG alpha term will go away. So this will be the general form for straight translation that we'll use. We may also cover curvilinear translation. However, I'm not going to address curvilinear translation in this video. All right, so here are some types of straight translation problems that we will want to look at. First one I just call normal acceleration, and most of the time what we're going to be looking for here is what are the reactions? What are the normal forces at the support reactions of an object under translation by virtue of the fact that it's being pushed or accelerated vertically or pushed this way. The second type of problem will be vehicles. These are extremely common, and where we may have accelerating in this direction, we may have one center of gravity or two centers of gravity, and I've got some examples for that. The third example will be objects that are being towed or translated or going down a hill or something like that, and there may be some angles that will have to be dealt with. And so I've got an example I want to visit with you about that. The fourth example is tipping or slipping, and I'll address that in another video. All right, the first translation concept I'd like to consider is straight translation. In other words, we're just going to go in a straight line. And here we have a barrel on a little hand cart being pushed by a guy, and he's going to be pushing it in this direction. So our velocity is going to go in this direction, and our acceleration is going to be in that direction. And so what we're looking for here is it says determine the acceleration of the truck and the normal reactions of each of the four wheels. All right, so there are four wheels, two at A and two at B. We want to find out the max or the acceleration. All right, so here let's give the specifics. It weighs 600 pounds, has a center of gravity at G. It's being pushed forward with a horizontal force. If we draw a free body diagram of this thing, I just drew it as a box. We got some wheels here. And we're going to say that there's a normal reaction at A and a normal reaction at B, separated here by 0.5 on this and 0.1 or 1.0 here. And being pushed with a force of 20 pounds there. This is at a distance 4 feet, which is given here in the picture. All right. So if I look at the mass force, some of the forces in the x direction is equal to mass times acceleration in the x direction. There's no friction, so acceleration is pretty easy. In this case, I'm going to define positive as going to the left. Sometimes positive can be an arbitrary thing, so I chose this as going to the left as positive, as just for my convenience. That way I'm pushing in a positive direction and I'm accelerating in a positive direction. So some of the forces in the x is mass times acceleration in the x. So my forces, 20 pounds going that way. My mass is 600 pounds divided by 32.2 gravity, and I can solve easily for acceleration, and that is 1.073 feet per second squared. Next question is, what are the normal reactions at each of the four wheels? Well, a moment equation is required for that. So let's look at this moment equation. In this case, I want to sum moments about point A. I could sum moments about point B, and it doesn't really matter. Either one would work. Maybe even some other point. But let's do them about point A to start with. So sum of the moments about point A, right there, is equal to mass times acceleration of g in the y direction. So what are my moments? Again, on this side of the equation, on the left side, I want to put the forces times the distances. On the right side of the equation, I want to honor the equal sign. On the right side of the equation, I want to put the results of those forces times distances on the left side. So over here, it's basically just statics. So if I look at the forces about A, I got here, I got a gravity, and I got that, and I got that. So I got all three of those forces acting about point A. Oops, come here, pencil. Draw my little arrow right there. So let's list them all here. So I've got 20 times this lever arm of 4 feet, and that's going in the positive direction. This would be causing a moment about A in the counterclockwise direction, and I define counterclockwise as positive. B also has a counterclockwise positive moment, so I'm going to say that B causes B times this distance of 1.5 is positive moment. mg is going in the negative direction, so mg times 0.5 would be negative. That's going to be equal to my vector, my mass times acceleration vector, which will be, and it also has a lever arm, but let's just look at the picture. We have our mass times acceleration vector acting through the center of gravity. The lever arm between that and y is my y bar, and it's given in the picture as that is 2 feet. So I'm going to say that that is mass times acceleration, the vector, times 2 feet. It's very important that we get the sign, the SIGN, properly of these mass times acceleration vectors, and it's very important, obviously, that we include the lever arm. So let's just make sure on our sign of the mass times acceleration vector, I've defined counterclockwise as positive, and so if I look at A, we look at the same kind of concept here, that this is a vector, it's causing a moment, if you want to call it. It's the moment of the mass times accelerations. There's a mass times acceleration vector times that distance, and that is positive counterclockwise. So this vector over on this side is positive on that side. All right, with that then I can basically look at this whole equation. I know my mass, I know my mg, I solve for the acceleration, and the only unknown in this equation is going to be the reaction at B, and I can solve that as 173 pounds. The next thing is to find the reaction at A, and that's a simple statics kind of type of analysis. It really is dynamics, because we know that the sum of the forces in the y is going to be this barrel is not accelerating or decelerating in the y direction. So in the y, we say the sum of the forces is equal to 0, and then I can solve for A is equal to 426. All right, the next piece that I'd like to visit about on the same problem is not what's asked in the question, but this question: what pushing force is required to lift up the rear wheels? So you can kind of imagine, if I push this hard enough, it's going to tend to try to flip over. It's going to tend to lift up those rear wheels, and what we're looking for is how far or how hard do I have to push it in order for the reaction at B to be equal to 0. So the same free body diagram applies, and I'm going to say that again, I'm going to sum moments about point A, and I'll say that here I have my center, my mg point going in this direction, and my force going in this direction. In this case, B equals 0, so that I won't have to include that one in my moment analysis. So let's just see. If I say sum of the moments about A again is equal to my mass times acceleration of G in the x direction times y bar. Here's my y bar. So I got P times 4 feet minus mg times 0.5 feet. Again, that's going negative. This one's going positive. If I define my positive moment direction going that way, that's equal to my vector, mass times acceleration, and that's times y bar, which is 2.0 feet. And with this, with one equation, I can find out how much force it takes, what my force P is, to be able to oh, actually, I do need 2 more forces. I do need 2 equations. So I have, in this equation, I have P is an unknown, and I have acceleration as an unknown. So in order for me to get another equation, I have to do a force, sum of the forces in the x direction. So sum of the forces in the x, going this way, is going to be equal to my mass times acceleration. So in this case, P is equal to mag in the x direction. I can solve that for acceleration as equal to P over m. Plug that back into my moment equation. Now I have 2 equations, 2 unknowns, and I can resolve that for 150 pounds. P is equal to 150 pounds in order to lift up the rear wheels. So I hope that's easy enough to see. Oops, I didn't scoot that up there fast enough. We can also sum moments about another point, and here some of the moments about the center of gravity might be a convenient way of doing that. So let's say that we sum moments about center of gravity, and I'm going to say that here I'll have an A going up this way and a P going this way, and I know that those are going to be equal to 0. Okay? So what do I need to know? If I look at the sum of the forces in the Y, which I didn't actually put on here. Oh, no, I did here too, right there. If I do the sum of the forces in the Y direction, I got mg coming down and A going up, and those are the only 2 forces in the Y direction if B goes to 0, and that's the condition I'm looking for, is how much force does it take for B to go to equal to 0. So I can say that A minus mg is equal to 0, or A equals mg. If I do a moment equation about point G, I can see that P around point G has a lever arm of 2, and A about G has a negative lever arm of 0.5, and so I can say that P times 2 minus A times 0.5 is equal to 0. Two equations, two unknowns, and I get P is equal to 150 pounds. All right, so there's two related but kind of different ways to solve for how much force it takes to lift up the rear wheels.